today's lesson, we are going to find moment about an axis. In our particular case, we're going to find moment on a windsurfer. The problem is, find the moment on the boom of a windsurfer when a wind is applying 15 pounds of force in the I direction, 6 pounds in the J direction, and 10 pounds in the K direction. And for our particular case, we are going to establish X as the green axis, Y as the blue axis, and Z as this red axis. Let's understand the picture real quick. So we can see from this diagram that the boom, this red pole right here, is going up in the Y direction 8 feet, protruding in the X direction positively by 3 feet, and going backwards in the Z direction 1.2 feet, making it negative. The formula for moment about an axis is this Greek letter, which represents the unit vector of the axis. And we are going to dot that with the moment equation R cross F, otherwise known as the lever arm cross the force vector. In our purpose, we're going to start from the base of the board to the top. As we discussed in the beginning of the video, the board is going to the right 3 feet in the positive direction, since it's moving towards the right, going up 8 feet, still in the positive direction, since it goes up, and it's going back in the Z direction 1.2 feet, making it negative. So our measurement vector will be 3 feet in the I direction, 8 feet in the J direction, and negative 2 feet in the K direction. I representing the x-axis, J representing the y-axis, and K representing the z-axis. While we're looking at the axis vector, we might as well find the unit vector, which is this Greek letter right here. So to find the unit vector, we will have to take the square root and square each term right here. So 3 squared, 8 squared, and the negative 1.2 squared. And we take the square root of this. This will give us our magnitude. So our magnitude equals 8.628. To find the unit vector from here, we will divide each of our terms by this 8.628. So each term gets divided by this 8.628. This gives us our unit vector right here, which equals 0.348i plus the 0.927j and a negative 0.116k. What makes a unit vector is if you square all these terms and do the same thing we did here to get this magnitude, it will always equal 1. So now we know our unit vector and our axis vector. We only need one more thing in this equation, and that's our force vector. This will be pretty easy because it gets stated in the equation. So we see that 15 pounds of force is in the I direction, 6 in the J direction, and 10 in the K direction. There's no negatives mentioned here, so they're all positive. Thus making our force vector 15 pounds in the I direction, 6 pounds in the J direction, and 10 pounds in the K direction. As PEMDAS indicates, we are going to cross product first, R cross F, or the lever arm cross the force. In our case, the boom right here is being applied a force of wind right around here, and that boom tends to rotate. So our lever arm, which is the boom, is our axis vector, which is a 3 feet, 8 feet, and negative 1.2 feet, and our force vector. So we will have to take the axis vector cross the force vector. To cross product, you will start by multiplying the first component in each equation. So this will be our 3 feet and our 15 feet. However, since these are both in the same direction, these will cancel out and become 0. Then you'll start multiplying the first component of the first equation by the second component, so our 3 times 6, and then so on with our 3 times 10. So we'd have a 0 in the I direction since it's in the same direction. 3 feet times 6 feet gives you the 18, and when it's in positive I direction and positive J direction, you'll get a positive K direction. Then when you multiply the positive I direction with the positive K direction, you'll get a negative J direction. Now, after we looked at the first component, we are going to look at the second component, the 8 feet in the j direction. So you start by multiplying the 8 feet by the first term in the second equation. So that would be the 8 times the 15, and then the 8 times the 6, and then the 8 times the 10. This will give us negative 120k. So 8 times our 15 gives us 120. And when you multiply positive j by positive I, you get a negative k. Then we will multiply our 8 feet by our 6 feet, but notice that it's in the same direction, giving us 0j. Then you multiply the 8 feet by 10 feet, which gives us positive 80 in the I direction. So our 8 feet positive in the j direction and our 10 feet positive in the k direction gives us a positive I value. And now we will work with our last component, the negative 1.2 feet in the k direction. We'll start off by multiplying 1.2 times 15. We're going to multiply the positive 1.2 instead of negative, since the negative just represents direction. So 1.2 times the 15, and then 1.2 times the 6, and then 1.2 times the 10. So when we multiply the 1.2 times the 15, we get 18. And when we have a negative k direction and a positive I direction, we get a negative j direction. Then when we multiply 1.2 times 6, we get 7.2. When we multiply negative k, when we have a negative k direction and a positive j direction, we get a positive I direction. And again, when we multiply the two k's, those come out to be equaling 0. So when we look at this equation, we see that there's some common terms here, and so we can combine these common terms. When we combine these common terms, we get a simplified version of 87.2 in the I direction, negative 48 in the j direction, and negative 102 in the k direction. So now we figured out the cross product, this r cross f. Now we will work with the Greek letter dotting to this cross product value. So for the dot product, we will use the axis unit vector. As we mentioned before, this Greek letter represents that. And we will dot that with our cross product solution right here. So it will be our axis vector dot our cross product solution. When we dot something, it's a little different. We saw in the cross product, when you multiply two things in the same direction, they equal 0. Instead, in the dot product, you only multiply things in the same direction. So in this case, we will multiply the two I directions. So this 0.348 times this 87.2 will give us a value. And when we dot product, this gets rid of the units, so the I direction will no longer be there, which giving us 30.346. Then we continue to dot the j's, so the 0.927 and the negative 48. That gives you a negative 44.5. Again, those j's cancel out when you dot. Then we do the same things with the k's, giving us a positive 11.832. With all these values, we now can simplify this and add them all together, giving us our final solution. The moment about this boom equals negative 2.331 foot-pounds.